Good afternoon, class, and, and welcome to our session. We are about to get started. Before I get started, I want to assure you all that no one is in jeopardy of failing who has been coming to class and who has been participating. I understand that this model of teaching is not the most effective. I understand that. And I'm not going to put the burden on you students. So what I'm going to be looking at in a more favorable manner is your attendance, your responses. In other words, I'm giving a lot of credit to those of you who are here each day. You're here on time. You remain here to the end of the session. You sign out, which means that you are attentive. So that is going to play heavily in your final grade. So be assured, if you have been doing those things, that you are not in jeopardy of failing. You're not even in jeopardy of getting a C. Now, that doesn't mean that I'm not going to count the quiz grades and the homework grades and the exam grades. I am going to count that. But I'm hoping that over these next few weeks that I can help you to learn what I know will demonstrate that you are capable, that you have earned an A or a B. So I need for you to demonstrate that. It's not enough that you have been in class and that you've been attentive, which is going to count favorably, but I still need for you to show that you are learning the material. And so with that being said, I want to pull up another assignment that I'm going to give to you. And I'll make it due, say, next Tuesday. So everything that I'm going to give you today and tomorrow will be for next Tuesday, because I know that we have next Monday off. How many of you have already enrolled for the fall semester? And how many of you feel certain that you will be returning in the fall semester, even if we have to continue in this online format? Can you please just go into chat and let me know if you are continuing at A&M in the fall, even if we are continuing online? I want to have some data to pass on to my chairperson about what I'm seeing and what I'm hearing from students. If you can go into chat and tell me that if you are still uncertain or if you're planning to come back, just let me know that. With that being said, I am going to go to the screen and we're going to work out some problems. And I want to show you how the review that we have been doing is preparing you to demonstrate that you have mastered some content in this class. So I'm going to go to the assignment that I'm going to be sending you. So this is the homework on chapter 6. So if you remember then, in chapter 6, we were talking about work and energy. So I'm going to go down to a problem at the very end, just to see if we have mastered something. So let's go down to problem number 20. Can everybody see problem number 20, yes or no?
Yes.
Okay, great. And also, have you all signed in? It's 1:35, so I'm giving extra credit to those who are here about 1:35. So have you signed in already? If not, do so right away, because my clock says 1:35. Okay, so let's use this problem, and let's just go through it very slowly to see how we're going to solve it. So it says, use the work energy theorem. So that tells me then that if I had my equation quiz out, I would say the work energy theorem says that work is equal to change in kinetic energy. That's the first thing I'm going to start with. Okay? That's the first equation. The second equation that comes to my mind is, what is work? Well, work is force cosine of theta times the distance. And sometimes the author uses S, but we know that the variable isn't a strict variable. It's just that we know that it stands for distance. We can use S, we can use X. It just means that the distance that the object moves. Then we also know that kinetic energy is 1/2 mv squared. So those are the things that we should have in our repertoire of equations that we're going to use even before we begin the problem, because we know that the work energy theorem says that work is equal to change in kinetic energy. Therefore, we must know the equation for work and the equation for kinetic energy. So now we're ready to write down the given. Okay. To find the force required to accelerate an electron. So we're given an electron and we're given its mass. Its mass is very, very small. Okay, so this mass is 9.11 times 10 to the minus 31 kilograms. Now, I want to explain. I am intentionally writing this down very, very slowly. And the reason why I'm doing that is because I want to incorporate several things in this one lesson. Okay, moving along the x-axis from so many meters per second. So that means that is my initial speed. My initial speed, and let me just give myself a little more space here. My initial speed is 4.00 times 10 to the 6 meters per second to my initial speed now, my final speed, okay, from 1.6 times 10 to the 7th meters per second, and a distance of, so my distance then is 0.0125 meters. Now immediately, I want to write this number in scientific notation because I want to be able to use my rules of exponents efficiently. So that means I'm going to move this over 1, 2. That means I have 1.25, and because I want this number to be written in the correct scientific notation, I stop at 1, 2. So this is minus 2 meters. In other words, it's not positive 2, it's minus 2. Because when I move it back, I'm going to move it back 1, 2. So I rewrite that number in that fashion. So now I have all my given. It's looking pretty good. Okay, now let's begin with the work energy theorem. Oh, I'm sorry. And it tells us, wait a minute, my pencil's not responding. Hold on. Give me a minute. My pencil's gone out. Hold on. I'm having a little technical difficulty here. Okay, hold on. Uh-oh. Hold on. For some reason, my pencil that is not responding. This is a new pencil, so I'm not sure what's going on. Give me a minute, please. Oh, well, that is not good. Let me turn my pencil off and on again and see what happens. For some reason, it's not even responding. Okay, give me a minute. Well, class, I seem to be having difficulty with my equipment here. Okay, let me go and see if I can't connect my pen again. Okay, just hold on for a few minutes. I'm going to go into my software and see why my pen is not responding. Just give me a minute to go and do that. Okay, class, I'm back. Unfortunately, I was not able to get this pen to work. So let's just see if I'm able to do this problem on the whiteboard with where I have more space, and we'll see what happens. If you're not able to follow along, then we may have to just wait until I can get this pen repaired or replaced. But let's just try it. So I'm going to go to the whiteboard. That was my practice trying to see if I can write it with just my finger. Oh goodness. Okay, so let's see what's happening now. Um, okay. Okay, so we have the mass. Oh no. Let me try my finger. The mass of an electron. So we said that was 9.11. No, this is not going to work. I just cannot control it. It's not right this way. Okay, the mass of an electron, 9.11 times 10 to the minus 31 kilograms. I can't see how this is going to work. Okay. So let me just start with this then. Work is now my now my fingers ain't even working. F cosine of theta d, which is change in okay, class. Okay. Let me just see what else we can do with our time today because this is not working out. Let me see what else we can do with our time. Let me see. Okay, let me see. Okay, did I charge my pen? Is there a way to charge your pen? There's no, it didn't come with a charging utility. I mean, equipment. It just the pen came. There wasn't any way to charge it. I may need to put a new battery in it. I don't know. I have used it quite a bit, but I thought it would last longer than that. This is a new pen that I purchased to be able to teach this class. Okay, they use batteries. All right, so I do need to check into that. Okay. I don't think this particular one has a charging mechanism. I bought this pen, then I sent it back, and the first one I got wasn't working, and then this one has worked well up until this very moment. And I went and tried to reconnect it, and it didn't seem to. Let me try one more time. Hey, look at that. Okay, I tried it again. Okay, let's just try it again, class. Let's see how far we can get. Okay, we'll just go back to the problem now and see if we can't see what's going on. This thing is really crazy. Okay, let's just try it one more time. Sorry about that, but it seems to be working again. Okay, so what we said was, oops. Hold on. You saw I was just writing on the board. Hold on. Let me just try one more time. We're not going to give up. Now I'm stuck with this thing. Okay. Whew, hold on. Let's just be patient. I think I'm going to get something done here. Okay. Something is strange, but let me just see. Annotate, pen, draw. Okay, we're back in business. Okay, if we can get through this problem, we'll be doing well. All right, so we have the mass. 9.11 times 10 to the minus 31 kilograms. The initial. I'm just going to put this because, of course, we know that it has 3 sig figs, but writing it down, you don't have to do all that. The final 1.6 times 10 to the 7th meters per second. And then we already wrote this distance in scientific notation, which we said was 1.25 times 10 to the minus 2 meters. Okay, now using the work energy theory. So that says that we begin by saying work is change in kinetic energy. Now, once you say that, class, once you understand what that means, see that's the physics right there. That is your physics. And the rest of this is just algebra. It's just methodically moving through the algebra. So work is change in kinetic energy. So what is work? Work is, and okay, what we're looking for, it says to find the force. So that's my unknown. The force is my unknown. Now, accelerate an electron moving along the x-axis. So it's moving along the x-axis. So we know then that the theta is just 0 because it's moving in the same direction. And the cosine, okay, theta is 0. And we know that this implies the cosine of 0 is 1. So since the cosine of 0 is 1, then my work is just force times distance, and that's equal to the change in the kinetic energy, which means I have the kinetic energy final minus the kinetic energy initial. That's what it means, change. So this is the force I'm looking for. So that means then that my force is equal to the change in kinetic energy final minus the change in kinetic energy initial divided by this distance. So as you can see, all I have to do now is do my algebra correctly. So what is kinetic energy final? That means I have mass times velocity final squared 1/2. Okay, that's the equation. KE is 1/2 mv squared. Okay. And minus 1/2 mass times velocity initial squared. All of that is divided by d. Now, let's simplify this algebra because what you see right away is that 1/2 mass is 1/2 mass is also in both of these terms. It's a factor in both of these terms. So I can factor that out. And of course, 1/2 of anything means that I'm dividing by 2. So to simplify that, I'm going to say that I have mass over 2. I'm factoring that out. Okay. Then in my denominator here, I still have D. And then my numerator here, I factored out 1/2 mass. I put 1/2 mass. I factored that out. So I have V final squared minus V initial squared. So now it's just a matter of doing this math correctly. And we know now that mass is given, distance is given, V final is given, V initial is given. So I'm going to do this work. But I want to show you another little trick very, very quickly so that the problem can be even easier to manipulate. And one thing I want to show you is, you see, this means that I am going to be adding, or in this case, subtracting exponents. And it's easier to do that when the exponents are the same. So that means I'm going to come right here and make this number, since this is times 7, or I can even make this number be times 7, either one. I mean, I can make both of these 6 or both of these 7. And you'll see the logic behind it. And this is just a trick I'm showing you that will make the problem easier, because that way you have to be trying to expand these large numbers. So watch this. Let's just make this number here, okay, point, oh goodness, 0.4, okay. In other words, this means I find my decimal and I go 6 times. If I move it over 1, 0.4, then I have to move it 7 times, meters per second. And you'll see, so this is now a 7. So that means then when I plug this in, if you don't mind, I'm going to go up here. I have mass 2 times my distance. And here I've got 0.4 squared times 10 to the 7th, okay, squared, meter per second squared. In other words, everything here, V final. Oh, I'm right here. Forgive me. Hold on. I put the wrong one. Give me 1 minute. Okay, forgive me. I put the wrong one. It's supposed to be V final, right? So V final is 1.6. So I got to put 1.6 squared. Now, I know you have your calculators, and I know you're going to put that in the calculator, but I'm doing this on purpose because I want you to see the logic in the math. So I have V final squared. So V final is 1.6, has to be squared. 10 to the 7th has to be squared. Meters per second has to be squared. Minus, now I have 0.4. That has to be squared. Times 10 to the 7th, that has to be squared. And meters per second, that has to be squared. So in my calculator now, before I even do that work, I notice then that I have common terms here, which I can factor out. In other words, before I even put it in my calculator, I have the mass over 2D, okay? And that's being multiplied by, now look, this term and this term is the same. So it can be factored out either at the end or at the beginning. So what I have now is 1.6 squared minus 0.4 squared. 10 to the 7th squared is, in both of these terms, that's going to give me what? 10 to the 14th. I'm factoring it out of here. Meter square, second square. I'm factoring that out of both. Meter square, second square. Now my problem is easy because now this number and this number, I can see it more easily. So let's go to the whiteboard and let me show you, because I know what you're thinking. You're thinking, I'm just going to put these numbers in my calculator and boom, that's my answer. But a part of this course is for you to learn how to recognize the need to have a common denominator, the need to be able to factor out common terms, and the need to be able to simplify the problem. Now, I said I went through this kind of slowly, but once you learn it, you won't go through it this slowly. You go through it much quicker than that because you won't even write it down. You'll know that if I move this number over and make it 1/10, this gets bigger by 10. I got 7 square and 7 square. I'm going to just do that all in one step, but I was showing you that step so you can be able to see it. So now I am going to come down here and plug my numbers in. Hold on. I'm going to come down here. Okay, so I don't have a calculator, so let's just go ahead and put these numbers in. So my mass is, hold on. My mass is 9.11 times 10 to the minus 31 kilograms. 2, and my distance was 1.25 times 10 to the minus 2 meters. Then I had 1.6 square minus 0.4 square. So what's that number, somebody? What is 1.6 square minus 0.4 square? Just put that number in my calculator. 1.6 square minus 0.4 square. Okay, so I got 2.4. Let's see what somebody else got. Let's make sure. Okay, very good. Okay, so very good. So that means then that we all got from this right here, we got 2.4. And then we have 10 to the 14th, and we have meter square second square. Okay, so now let's just do the number part of the equation before we even do the exponent part, because see, all these numbers are distinct. So we can see we have the number part right first, and then if we don't have that part correct, then we can see we have an error somewhere. So we have 2.4, and I'm going to multiply that by 9.11. Okay, get that. We're going to divide that by 2, and we're going to divide that by 1.25. And we get 8.746. So the number part that we get, even before we do the rest of the exponent, we get 8.7456. Okay, 7456. Before we even do all the rest of this part of the equation, we see that our answer is possibly going to be what? A, even before we do the rest of it, because this number is unique only to this number if we round it up by 1. But let's just see if our exponent part is correct. So now we have minus 31 over minus 2 times positive 14. So we take this minus 2 up to the numerator, then we have what? We have 10 to the minus 31 times 10 to the positive 16. Okay, now we need to have newtons. So let's see what our units are. Our units are kilogram over meter. And here we have meter square over second square. So this meter will cancel one of those meters, and we'll get kilogram meter per second square. And that's our Newton that we're looking for. So we should be in good shape. And not only that, we see that a negative 31 and a positive 16 will give me a positive what? I'm sorry, this would be negative because this is a larger number. 31, that'll give us a what? A negative 15. So now I want to use this one problem to show you how to methodically work through this problem. So when we solve for our force, here, and we will get 8 point, because this is a 5, this rounds up to a 4, 75 times, we have minus 31, positive 16, we got 10 to the minus 15. And then we have kilogram meter per second square, and that's a Newton. Okay. All right. So that's the type problem that we want to be able to demonstrate. So if in the final exam, I give you, say, a proton, okay? Proton's mass is 1.673 times 10 to the minus 27. I can change these numbers from this number to 3 to the 10 to the 6th up to 7 times 10 to the 8th. I can give you any numbers, but I want you to be able to work it through, not just put numbers in your calculator. You see, this is what we are finding, that our students are relying on the calculator. And if they put all this in incorrectly, and then they don't get one of these answers, then you got to just try to guess, do some kind of educated guess. But you rather be able, and I want you to be able to work it through like we did in this problem. Now, let's see if you have any questions about what I did in this problem. Any questions? Okay, no questions. Does everyone understand? Can everyone do this type problem in the final exam? I give you this type problem in the final exam and I say, show your work. Will you be able to solve this problem? Yes or no? In the final exam. Okay. Okay. Nigel said yes. Keston said no. Okay. Now, if any of you are thinking that your answer is going to be no, then let me tell you what you have to do. You have to take this very problem and work it through several times until you understand the steps that we're taking and why. That's what your job is. Learning takes place with practice. Even if I go through it again the exact same way, it doesn't mean that I'm going to help you to learn it by me going through it even, 2 more times. It means that you've got to sit down, begin with the given, and work it through step by step until you are able to see what it is that you must do and understand in order to solve the problem. So that's why I chose a problem like this, to emphasize that point, because unless you put in the time, you're not going to be able to get that A or B that I'm looking for. Because like I said, the physics was right here. This part right here represents the physics. And everything else after that is just algebra. And that's why I wanted to go through the algebra, to make sure you understand what is being done. Now, if you start to go through it and you don't understand what the next step is and why, that's where I want to assist you. But I won't be able to assist you there if I don't know what it is that you don't know. So going forward, I need for each of you to not be shy. I really, really, really need for you to let me know what you don't understand. That's the only way I'm going to be able to help you. And if we were in a classroom, I could come to you individually and say, okay, I see you are not putting down on your paper what you need to be putting down to solve this problem. But I can't see that now in this environment. That's why I need for you to be honest. Let me know what you don't understand. So you have this in your notes. You see what you've been following along. You must tell me now, and you can text me or call me where it is in this process that you got lost. And that's where I want to help you. Okay, let's go to another problem. Okay, let's choose a simple one first, and then let's choose a more difficult one. Let's choose a simple one now. Let's choose number 17. Let me I'm trying to make enough space. Okay, let's choose a more basic one, number 17. Okay, so now, okay, the kinetic energy of a truck. So my kinetic energy of a truck whose mass is given is 1,800 kilograms. Okay. The kinetic energy is joules. So we have 7.2 times 10 to the 5th joules. And the question is, what is the speed of the truck? So we're looking for V. So we began with our equation for kinetic energy. And kinetic energy is 1/2 mv squared. So clearly we're looking for this V. So by this time in our lecture, you should be able to say that V is the square root of 2 times the kinetic energy divided by the mass. At this point, you should be able to quickly do that. And if you do that quickly in your calculator, you're going to be able to put these numbers down quickly. But now, let me show you again how you want to reduce this, okay? So you have 2 times the kinetic energy. So you have 2 times kinetic energy is 7.2 times 10 to the 5th joules. And I'm going to divide that by the mass. And the mass, I'm going to write my mass as 1.8 times 10, oh goodness, 10 to the what? 1, 2, 3, 10 to the 3rd. Now you may ask yourself, why did I do that? Well, one reason why I did that, class, is because I know that 5 minus 3 is 2. And I know that the square root of 10 squared is just 10. So you see, I'm using that tool that's in the back of my head to make this problem easier to solve. Because if I know the square root of 10 squared is 10, I can just factor that out already. Okay? And that way, I'm not having to deal with any of this stuff. Okay, now, 2 times 7.2, whatever that is, divided by 1.8. I can look over here before I even do my answer and see what my possible answer is. So even if, I mean, I'm writing this all down now, but hopefully as you move through, you won't be writing all this down. You will see it. Okay, so I've got 7.2 times 2. Oh, my calculator on. Hold on. 7.2 times 2. I got that. And I'm going to divide it by 1.8. I got that. And I'm going to take the square root. So second function, on my calculator, second function, I get the square root of my answer. And I get 2.82. Now, I got 2.82, but I'm going to multiply that by 10. So I look over here and I see what? 28. So I'm going to choose 28 even before I go and finish the problem out. You see, I'm not even going to finish this is an exam. So I'm not going to even be finishing all the problems out because I can see right away that this number corresponds to 2.8 times 10. So that's 28. So now I'm ready to move on to the next problem. But if I want to make sure that this was correct, I would even go ahead and make sure that my units give me meters per second. So I have a joule. A joule is a Newton meter divided by a kilogram. A Newton is a kilogram meter per second square. That's what a Newton is. And I have times a meter. I'm dividing by a kilogram. So kilogram and kilogram is gone. Meter square over second square, that's under the radical. So when it comes out, of course, it is meters per second. Under the square root sign, I have meter square second square. When it comes out, I have meters per second. That's the unit I'm looking for. So therefore, I have my answer. Okay. Please follow through on that question and see if you can understand exactly what we've done. This is the physics, and this is just the algebra. Okay, let's move on to another one. I'm choosing these problems so I can show you the physics and the math. Okay, let's look at one. I thought I had one that had both the potential energy and the okay, I don't see that problem. I meant to put the problem on there where you had to use the potential energy and the kinetic energy, but I don't think I put that problem on there. Okay, let's look at one like number 15. Okay. This question right here is a sort of a what we call a intuitive question, because the question says the kinetic energy of a car is 8 times 10 to the 6 joules as it travels along a horizontal road. How much work is required to stop the car in 10 seconds? Well, the amount of work that's required is equal to the change in the kinetic energy. And since we know that it goes from 8 times 10 to the 6 joules to 0, then we know what that work is. It's the change in what? The kinetic energy. So that means that it goes from 8 times 10 to the 6 down to 0. The change had to be 8 times 10 to the 6th. So that problem does not require you to do a lot of work. That problem just requires you to understand what is going on. So we said that the work The work is the change in the kinetic energy. Initially, the kinetic energy was 8 times 10 to the 6 joules. Okay, and it goes to what? It goes to 0. So that means that the change must have been the amount of 8 times 10 to the 6 joules. So now we're able to solve that problem without having to do a lot of work. Okay, that's what it means. Now this question says, how much energy is dissipated in braking a 1,000 kilogram car to a stop from an initial speed of this? So now we know that the kinetic energy needed, again, is the energy required to take a mass of 100 kilograms to initial speed of 30 to a final speed of 0. Of course, that's just what? The kinetic energy is 1/2 mv squared. So we just plug that in. That's one that's pretty simple. So let's see what you all get for that one. That's one of the ones we're going to have on a test that's very straightforward. Doesn't even require you to write it down other than know what the equation is. So my equation says, of course, that the kinetic energy required to stop it is 1/2 mv squared. Okay, what's that answer very quickly? Okay, so I want to know, do I have anybody in this class who quickly said mv squared? This is my v, so I've got 900 here. 1/2 of this is 600 here. So I got 9 times 6, that's 54, and I got 1, 2, 3, 4 zeros. So without even having to pull out my calculator, I'm going to choose this answer. I hope you can see that, because if you don't see that, that means that we're not moving quickly through our math skills. In other words, this equation you can do in your head. I didn't even put in a calculator. You got 300 squared, that's 900. That's 30 squared, that's 900. 3 squared is 9. And you got 0 twice, because when you squared, you got 2 zeros. Over here, you got 1,200 1/2. So that's 600. 6 times 9 is 54, and I got these 4 zeros. That's the type of problem I put on the exam just to see if you can't move through it quickly. Okay. Okay, let's go up to a thought question. One that doesn't have any numbers. Let's go up to okay. In which one of the following situations is zero net work done? So now, zero net work. Well, first of all, we have to remember what work is. So we know that work is force through a distance. Now, in this case, we may have to break down force. And the reason why is because of what they're telling us in this problem. Falling down, pulling, and all that. So we know that force is Newton's second law, mass times acceleration times d. So we're trying to see, okay, does the object have mass? Yes. Does the object move a distance? Yes. Is the object accelerating? So these are the three things we're looking for. So, in which one of the following situations is zero net work done? Zero means that when I multiply these three numbers together, I get 0. Okay. A ball rolls down an inclined plane. It has mass, it's accelerated, and it has distance. A physics student stretches a spring. Okay, we have mass, the spring, we're moving it from its initial velocity is changing to some other velocity as we move it, and it's moving some distance. A projectile falls towards the surface of the earth. Okay, it's accelerating some mass through some distance. A box is pulled across a rough floor at constant velocity. Okay, that's a good term for us to explore, because constant velocity means the object is not accelerating. Whatever it is, it's not accelerating. So that means that my A in this case is 0. And whenever I multiply anything by 0, that whole thing becomes what? 0. That's what it means. We have to evaluate each one of these. So if I find one that has 0, that means 0 net work done. So in that case, I'm going to choose D. Okay. Complete the following statement. Work may be expressed using all of the following units except one. And even if I don't know what an erg is, at least I know that watt is the unit for what? Power. So I'm going to choose that simply because power and work aren't the same units. So because I know what a watt is, I'm going to choose what? E. Okay. Let's go down to number 3. You can stop me at any time. Just go into chat and just tell me if you don't understand or not. Let me go see if anybody has any questions in chat. Okay, no questions so far. All right, good. Okay, let's go down to number 3. Okay, let me make some space. Okay, making some space. All right, here we go. Number 3. A concrete block is pulled 7 meters across a frictionless surface by means of a rope. Okay, the tension in the rope is 40 newtons. And the net work done on the block is this. So first we're going to analyze this problem by writing down what is given. So it moves a distance. So we know what that distance is. That distance is 7 meters by means of a rope. The tension in the rope. So that means that the tension now is my force. Tension is a type of force. And this force right here is 40 newtons. Now, we know that if it's moved across a frictionless surface, it's moving horizontally. So that means then that the force that's moving it across here is going to be F cosine of theta. That's the force that's moving it. And the work done, they tell us, is 247 joules. So we go to our equation for work, and that equation says that work is F cosine of theta times the distance. And look, we know work, we know F, we know D, and we need to find what? Cosine of theta. And once we find cosine of theta, we can find theta. So we say then that the cosine of theta is equal to, we're multiplying by force, multiplying by distance, means we're going to divide by that. So we have work divided by force times the distance. And now we're going to plug this in. So my work is 247 joules. The force that's given here is 40 newtons. And The distance that's given is 7 meters. Now, a Newton meter is a joule. The important thing here is that these units need to cancel out. That's your clue that you're on the right track because the units need to cancel out. So since a joule is a Newton meter, then all these units cancel out and I'm left with just a number. And that number is 247 divide 40 divide 7. So let's do that. 247 divide 40, and we get 6.175, and then we divide 7, and we get 0.88. So you should all be getting 0.882. Make sure everybody got that. Let me see what somebody else got. Let me see. Chat. Okay, very good. Nigel got that. So if Nigel got that, I hope that the others can get that. It shouldn't be difficult to get that number. Okay, so once you get that number, that is the cosine of theta, whatever theta is. So now in your calculator, since you have that number, you're going to say, okay, theta is an angle whose cosine I know to be what? 0.882. So that number is already in my calculator. So my calculator, I'm going to say second function inverse of what? Of cosine. So in my calculator, I see cosine -1. Now, I can type this number in, or since it was my last answer, I can just say second function answer, depending on how your calculator works. And when you enter that, you will get 28.09. So that means then that theta is 28 degrees. So let's see if anybody got that answer. Okay, very good. All right. So the rest of you should get that too, because I see that Kaylin and Lex also got 0.8821, which is very good. So now you're ready to find the actual theta, because the answer said, what is theta? Now, in an exam like this, I'm going to tell you some of the things that I'm going to be testing you on. I'm going to be testing you to see if, for example, over here in these choices, I may put in this number, 0.882, or it'll be a different problem, but I may just put in this very number because many students, once they solve for something and they see it over in the answer key, they choose that. But you see, we're not looking for a cosine of theta, we're looking for theta. So that means you have to go one more step and find out what is the angle theta, not the cosine of theta. So keep that in mind now in the final exam so that you don't trip up by not answering the question that's being asked of you. I want to point that out because this is where I see, and students say, oh, Dr. Edwards, you're just trying to trick us. That's why you put that wrong answer there. No, I am not trying to trick you. I'm trying to force you to think, because that is what this exam will be all about, and that's what this course is all about. Can you think through the problem? Okay, let us look at another one. I think we have time for one more. Let's look for another one that's just what is the I'm trying to find one. Okay, here we go. Okay, let's look at number 11. Which one of the following statements concerning kinetic energy is true? Okay, kinetic energy can be measured in watts. Definitely false, because energy is measured in joules. kinetic energy is always equal to the potential energy. That can't be true because we did the problem where if you start at a height and come down, the kinetic energy is increasing while the potential energy is decreasing. So that definitely can't be true. Okay? Kinetic energy is always positive. And let me show you why that is always absolutely true. Let me show you why that's always absolutely true. Okay? Let's look at my definition for kinetic energy. Kinetic energy is 1/2 mv squared. So that means then that mass, which is a scalar, you can never have negative mass. It does not exist. So that means that the only way for kinetic energy to be negative and not positive is that v squared is negative. But we know that any number squared will be a positive number. Even if I have my velocity moving in, say, a negative direction, which means it's moving in this case to the left. So that means then that v could possibly be negative, say 2 meters per second squared. Per second, not squared. Of course it's not squared. Forgive me, hold on. Okay, but when I square that, of course, I'm going to get what? 4 meter square second square. So that means then that the kinetic energy can never, ever, ever be negative. So just by understanding that, it says which one is true, I can stop right here because that is definitely true. Okay. So these are the type questions I want you to finish answering. We've answered some of these. And again, if you need help with anything that you're doing, I really need for you to contact me. So I can help clear up some small thing that you are not being able to understand. Now, let me give you a good question. One like number 14. An experimental 15 kilogram car travels at constant speed of 22 meters per second around a circular track that is 80 meters across. Now, what is the kinetic energy of the car? So the thing that you're looking at here is not just the constant speed, which is one thing you're going to look at for sure, because constant speed tells us what? What does constant speed tell us? That the object is not accelerating. But remember, we discussed this part around a circular track. So that means that even though the object's speed is constant, we also know in this case that the acceleration is not constant, because acceleration is both what? Magnitude and direction. And also we know that for an object that's moving in a circle, it does have acceleration. The acceleration for an object that's moving in a circle is called centripetal acceleration. And that is v squared over what? Over r. So that question means then that you cannot assume just because you see the term constant speed that their acceleration is 0. So unlike when it's moving in a linear path, where if there is acceleration, if v is constant, then of course a is 0. But in a circular path, v can be constant, but since it's centripetal acceleration, we have to do what? V squared over r. So that means then it says, what is the kinetic energy? And we we think about it like that. Now, because we're given the kinetic energy is 1/2 mv squared, we're given v, and we're given what? R. We ask ourselves now, what's that problem asking me? Because it still is not telling me that my acceleration, I mean, I can solve for the acceleration, but that's not what goes in this problem. So now, what is the author asking us? Give me just 1 minute to see what this person wants on my phone. Give me okay. So since it did give us my velocity, and it did give me my mass, and even though it gave me the radius, this R is not telling me to look for the centripetal acceleration. It's simply telling me that it has centripetal acceleration. So therefore, I cannot say that it's constant speed. So with that in mind, then I just take my 22 and I do what? I square it. I multiply it by 1,500, or multiply it, in this case, by 750, and I have my answer. So let's see what our answer is for that problem. So I have 22 squared, and I get that, and I multiply that by 750, and I get 363,000, and I write that as 3.63 times 10 to the 1, 2, 3, 4, 5. 3.6. Okay, there we go. All right, let's see what somebody else said. Okay. Now, I'm looking at Kaylin. Okay, look at Kaylin, and look at your answer again, Kaylin. Nigel, that looks good. Okay. Now, Kaylin, even though you need to look at your answer again, I'm glad that you are responding. That's what I'm looking at. I'm looking at to see who's responding, because I'm thinking that if you're not responding with some answer, that you're not even there, especially for an easy problem like this. Okay. I'm going to go ahead and close, because I know that we're going over. Don't want to go over. It's 2:46, but I'm going to send these problems to you. And even though I've given you some answers, I want you to work through and get these answers. Okay. All right. You can sign off as you exit.